JavaFX architecture. Here you can see architectural diagram of JavaFX. JavaFX is a software platform for creating and delivering desktop applications as well as rich web applications that can run across a wide variety of devices. JavaFX has support for desktop computers and web browsers on Microsoft Windows, Linux, and Mac OS, as well as mobile devices running iOS and Android. Now we are focusing on JavaFX public APIs and Scene Graph. JavaFX public APIs. The top layer of the JavaFX architecture provides a complete set of public APIs that support rich client application development. These APIs provide unparalleled freedom and flexibility to construct rich client applications. The JavaFX platform combines the best capabilities of the Java platform with comprehensive immersive media functionality into an intuitive and comprehensive one-stop development environment. Scene Graph. The JavaFX Scene Graph is the starting point for constructing a JavaFX application. It is a hierarchical tree nodes that represent all of the visual elements of the application's user interface that can handle it can handle input and can be rendered. Here you can see a JavaFX application lifecycle. The entry point for JavaFX applications is the application class. The JavaFX runtime does the following in order whenever an application is launched. 1. Construct an instance of the specified application class, calls the init method. 3. Step 3 calls the start JavaFX.stage method. Stage 4 wait for the application to finish, which happens when either of the following occur. The application calls platform.exit method. The last window has been closed and the implicit exit attribute on platform is true. Step 5 calls the stop method. Note that start method is abstract and must be overridden. The init and stop methods have concrete implementations that do nothing. Calling platform.exit method is the preferred way to explicitly terminate a JavaFX application. Directly calling system.exit int method is an acceptable alternative but doesn't allow the application stop method to run. JavaFX A JavaFX application should not attempt to use a JavaFX after the FX toolkit has terminated or from a shutdown hook, that is after the stop method returns or system.exitInt method is called. Here you can see launch is connected to init and init is connected to start and start is connected to stop. Here you can see root, branch and leaf nodes. This figure shows a general inheritance diagram of root, branch and leaf nodes. The root node has 2 leaf nodes and 1 branch node. The branch node has 2 leaf nodes. The JavaFX Scene Graph API makes graphical user interface easier to create, especially when complex visual effects and transformations are involved. A scene graph is a tree data structure most commonly found in graphical applications and libraries such as vector editing tools, 3D libraries, and video games. The JavaFX scene graph is a retain mode API, meaning that it maintains an internal model of all graphical objects in your application. At any given time, it knows what objects to display, what areas of the screen need to repainting, and how to render it all in the most efficient manner. Instead of invoking primitive drawing methods directly, you instead use the scene graph API and let the system automatically handle the rendering details. This approach significantly reduces the amount of code that is needed in your application. The individual items held within the JavaFX scene graphs are known as nodes. Each node is classifies sorry. Each node is classified as either a branch node, meaning that it can have children, or leaf node, meaning that it cannot have children. The first node in the tree is always called the root node, and it never has a parent. Here you can see the root node here, and root node is connected to leaf nodes and a branch node here, and branch node is connected to leaf nodes here. Here you can see the scene graph consists of a window, stage, scene and its nodes. A scene describes everything that is inside a window in a JavaFX application, where the window provides a look and feel that is that's specific to the OS that's driving the application. The scene is completely yours to style and change. The window that most people will use is a stage, which extends the window class. Each of these concepts, stage, scene, scene graphs, and nodes, surround the scene object, and together they discharge the responsibility of rendering your application to the screen. Stage. The stage represents the window of any view in the JavaFX model. In fact, it extends the window. Scene graph. The scene graph in JavaFX represent the contents of a scene that focuses on the hierarchical relationship between nodes. Prism rendering scene graph. Alongside the scene graph, we get to see and modify. JavaFX maintains a sister scene graph and uses this to determine almost other things. How much of the scene has changed and which areas of the scene need updating. The textures required to render the scene and the rendering of the scene. Part of the reason that the JavaFX scene can be so efficient is that it caches and unchanged elements of a scene, so they don't need to be recomputed unnecessarily. Nodes. Nodes are the foot soldiers of a user interface. From charts to images, layouts, to shapes, they all extend the node class in some way. The node is the basic interface component that has bounds, layout position, event handling, mouse, keyboard, etc., opacity, and transforms. All other UI elements layer functionality on top of the node class. Scene is responsible for four things: holding a reference to the parents that hold the scene nodes, that is most often a layout of some type, but can be a group. Optionally controlling the size of the window that can be delegated to the root node, but doesn't have to be. Setting default higher level rendering properties, useful for 3D scenes and the camera also for 3D. Triggering event handling behind the scenes. For each of these things impacts how the scene works and how it needs to be defined. For instance, because the scene will hold your scene graph, it must to be defined with the root node. Anti-aliasing and depth testing correspond to higher level rendering properties which can be set as default for this the scene. Here you can see nodes must belongs to a group or layout parents. Nodes are connected to scene. Nodes interacts with scene. Scene holds all nodes in a parent and directs events. Scene interacts with stage. Stage extends window, handles UI centric styling and behavior. Here you can see a simple JavaFX application. The class application class from which JavaFX applications extend. This class is in package javafx.application. As an example 2, we can consider JavaFX application lifecycle here. Launch launch a standalone application. This method is typically called from the main method. It must not be called more than once or an exception will be thrown. This is equivalent to launch the class.class args, where the class is the immediately enclosing class of the method that called launch. It must be a subclass of application or a runtime exception will be thrown. Launch method does not return until the application has exited, either via a call to platform.exit or all of the application windows have been closed. Init the application initialization method. This method is called immediately after the application class is loaded and constructed. An application may override this method to perform initialization prior to the actual starting of the application. The implementation of this method provided by the application class does nothing. Note, this method is not called on the JavaFX application thread, an application must not construct a scene or a stage in this method. An application may construct other JavaFX objects in this method. Start. This method is called when the application should the main entry point for all JavaFX applications. The start method is called after the init method has returned and after the system is ready for the application to begin running. Note, this method is called on the JavaFX application thread. Stop. This method is called when the application should stop and provides a convenient place to prepare for application exit and destroy resources. The implementation of this method provided by the application class does nothing. Note, this method is called on the JavaFX application thread. Here you can see add an exit button to the scene here. As an example 3, we can consider JavaFX.scene package. Provides the core set of base classes for the JavaFX Scene Graph API. As an example 4, we can consider adding a leaf node. Class scene, the JavaFX scene class is the container for all the content in a scene graph. The background of the scene is filled as specified by the fill property. The class scene is in JavaFX.scene package. The important points to consider in this example are as follows. The main class is an extension of the JavaFX.application class. Its start method is overridden. In this case, overridden and receives a stage object, a top level GUI container as its only parameter. The root node, in this case, an instance of the JavaFX.scene.group class is created and passed to the scene constructor along with the scene's width, height and fill. The stage title scene and visibility are all set, the main method invokes the application.launch method. The blue rectangle leaf node that is 250 multiplied by 250 pixels will appear at the specified x and y coordinates. By default, x increases from left to right and y increases from top to bottom. This can be affected by transformations. However, this figure shows the results of adding a leaf node. As an example 5, we can consider this one as adding leaf nodes. Class scene here, the JavaFX scene class is the container for all content in the scene graph. The background of the scene is filled with as specified by the fill property. The node, the class node is the base class for scene graph nodes. A scene graph is a set of tree data structures where every item has a 0 or 1 parents. And each item is either leaf with 0 sub items or a branch with 0 or more sub items. This is scene and node class nodes are in package JavaFX.scene. Here the class circle is a subclass of class shape, and class shape is a subclass of class node. Here the class text is a subclass of class shape, and class shape is a subclass of class node. Here you can see a push integration. Here the method void run later runnable. The run the specified runnable in on the JavaFX application thread at some unspecified time in the future. The push communication is a request response style of communication without the request part. The application server can push out data at any time. The Java Message Service JMS, WebSockets and memory grids come with a fire and forget style notification mechanism and can be easily integrated with JavaFX. JSR 356 implements the WebSocket protocol, is a part of Java EE7 and comes with the Java Client API. The WebSocket specification introduces a bidirectional binary protocol and is perfectly suitable for integration of UI clients, WebSocket messages. UI clients. WebSocket messages can have a binary or text nature and are received with an endpoint subclass as shown here. As an example, we can consider this illegal state exception. If this method is called more than once, the method we consider here is void launch string ... args in class application. As an example 2, we can consider null point exception. If root is null in constructor scene parent root double width double height boolean depth buffer in class scene. As an error example, we can consider this error: access restriction. The type application is not API restriction on required library rt.jar. This occurred in the environment of with JavaFX and Eclipse. As an error example 2, we can consider this error occurred in JavaFX 8. Error 3525 Java method getScene in class JavaFX.stage.window cannot be applied to given types. Required no arguments. Found JavaFX scene.scene reason actual and formal argument list differ in length. Now we are focusing on quantum toolkit. Quantum Toolkit ties Prism and Glass windowing toolkit together and makes them available to the JavaFX layer above them in the stack. It also manages the threading rules related to rendering versus event handling. As an example, we can consider Quantum Toolkit class. This class is in package com.sun.javafx.tk.quantum. As an example 2, we can consider JavaFX 8 command line option quantum.single threaded. This option is default to false. As an example, we can consider illegal state exception. Throw when shutdown hook already removed. This exception can be thrown from void dispose in class Quantum Toolkit. As an error example, we can consider this. This is occurred in as an illegal state exception while using com.sun.javafx.scene.web.debugger. Nested event loops are allowed only while handling system events at com.sun.javafx.tk.quantum.quantumtoolkit.enter nested event loop quantum toolkit.java, etc. Now we are focusing on Prism, JavaFX high performance graphics engine. Prism processes render jobs. It can run on both hardware and software renderers, including 3D. It is responsible for rasterization and rendering of JavaFX scenes. The following multiple render paths are possible based on the device being used: DirectX 9 on Windows XP and Windows Vista, DirectX 11 on Windows 7, OpenGL on Mac Linux embedded, Java 2D when hardware acceleration is not possible. The fully hardware accelerated path is used when possible, but when it is not available, the Java 2D render path is used because the Java 2D render path is already distributed in all of the Java runtime environments, JREs. This is particularly important when handling 3D scenes. However, performance is better when hardware render paths are used. As an example, we can consider package com.sun.prism. As an example 2, we can consider this JavaFX 8 command line option. Prism.geforce GPU here. This force GPU, this basically forces a GPU if GPU is PS3 capable, disable GPU qualification check. This is default to false. As an example, we can consider this non-invertible transform exception. This can be occurred from base transform, extract 3D, remainder base transform xform method in class base shader graphics. As an exception example, we can consider this java.land.null point exception at com.sun.prism.impl.ps.base shader context.init lcd buffer at com.sun.prism.impl.ps.base shader context.validate lc d buffer, etc. Now we are focusing on Java 2D. Java 2D is an API for drawing two-dimensional graphics using the Java programming language. Every Java 2D drawing operation can ultimately be treated as filling a shape using a paint and compositing the result into the screen. Java 2D, when hardware acceleration is not possible, the fully hardware accelerated path is used when possible, but when it is not available, the Java 2D render path is used. Because the Java 2D render path is already distributed in all of the Java runtime environments, JREs. This is particularly important when handling 3D scenes. However, performance is better when the hardware render path is used. Here you can see rendering pipeline. Primitive, you can see here primitives and here graphics 3D, 2D, and output devices. In graphics through 2D, the rendering process can be broken into 4 phases that are controlled by the graphics 2D rendering attributes. The renderer can optimize many of these steps. Either by caching the results of the future calls or by collapsing multiple virtual steps into single operation, or by recognizing various attributes as common simple cases that can be eliminated by modifying other parts of the operation. The steps in the rendering process are: 1. Determine what to render. 2. Constrain the rendering operation to the current clip. The clip is specified by a shape in the usage space and is controlled by the program using various clip manipulation methods of graphics and graphics 2D. The user clips is transformed into a device space by the current transform and combined with device clip which is defined by the visibility of windows and device extents. The combination of user clip and the device clip define the composite clip, which determine the final clipping region. The user clip is not modified by rendering system to reflect the resulting composite clip. Determine what colors to render, and step 3. And step 4, apply the colors to the destination drawing surface using current composite attribute in the graphics 2D context. Uh, there are three types of rendering operations, along with the details of each of their particular rendering processes are shape operations, text operations, and image operations. In shape operations, step 1, if the operation is a draw shape operation, then the create stroked shape method on the current stroke attribute in the graphics 2D context is used to construct a new shape object that contains the outline of the specified shape. Step 2, the shape is transformed from the user space to the device space using the current transform in the graphics 2D context. Step 3, outline of the shape is extracted using getPathIterator method of shape, which returns a path iterator object that iterates along the boundary of the shape. Step 4, if the graphics 2D object cannot handle the curved segment of the path iterator object returns, then it can call the alternative path iterator method of shape, alternate getPathIterator method of shape, which flatten the shape. Step 5, the current paint in the graphics 3D context is queried for the paint context, which specified the colors to render in the device space. Text operations. Step 1, the following steps are used to determine the set of glimpses required to render the indicated string. If the argument is a string, then the current font in the graphics 2D context is asked to convert the Unicode characters in the string into set of glyphs for presentation with whatever basic layout and shaping algorithms for font implements. If the argument is an attributed character iterator, the iterator is asked to convert itself to a text layout using embedded font attributes. The text layout implements more sophisticated glyphs layout algorithms that perform Unicode bidirectional layout adjustment automatically for multiple fonts of differing writing directions. If the argument is a glyph vector, then the glyph vector object already contains the appropriate font specific glyph codes with explicit coordinates for the position for each glyph. The current font is queried to obtain outlines for the indicated glyphs. These outlines are treated as shapes in user space relative to the position of each glyph that are determined by step 1. Step 3, the character outlines are filled as indicated in the shape operations. Step 4, the current paint is queried for a paint context which specifies the colors to render in the device space. Image operations. Step 1, a region of interest is defined by the bounding box of the source image. This bounding box is specified in image space, which is the image object's local coordinate system. Step 2, an affine transform is passed to draw image affine transform image observer method. The affine transform is used to transform the bounding box from image space to UC space. If no affine transform is supplied, the bounding box is created as if it's already in the UC space. Step 3, bounding box of the source image is transformed from UC space into device space using the current transform. Note that the result of transforming bounding box does not necessarily result in a rectangular region in device space. Step 4, the image object determines what colors to render, sampled according to the source to the destination coordinate mapping specified by the current transform and optional image transform. The default rendering attributes, the default values for the graphics 2D rendering attributes are: for paint, it's the color of the component, font, the font of the component, stroke, a square pen with the line width of 1, no dashing, segment joints and square and end caps. Transform, the default attribute, default value is the get default transform for the graphics configuration of the component. For composite, the default value is the alpha composite dot src underscore overrule. For clip, the default value is no rendering clip. The output is clipped to the component. Here you can see primitives, graphics 2D and output devices. Here you can see a shape is connected to stroke is connected to transform is connected to rasterizer, rendering hint is connected to rasterizer, and rasterizer is connected to clip is connected to paint, and paint is connected to composite is connected to screen and printer. In text, the text is connected to stroke is connected to font, and font is connected to transform is connected to rasterizer, rendering hint is connected to rasterizer is connected to clip is connected to paint is connected to composite, and composite is connected to screen and printer. In images, images are connected to transform is connected to rasterizer, rendering hint is connected to rasterizer is connected to clip is connected to composite is connected to screen and printer. Here you can see the graphics 2D class rendering context contains several attributes. Stroke, the pen attribute applied to the outline of the shape. These stroke attributes enable you to draw lines with any point size and dashing patterns, and apply end cap and join decorations to a line. The fill attribute is applied to a shape interior. This paint attributes enables you to fill shapes with the solid colors, gradients and patterns. Composite. The composite attribute is used when rendered object overlap existing objects. The transform attribute is applied during rendering to convert rendered object from user space to device space coordinates. Optional translation, rotation, scaling and shearing transforms can also be applied to these attributes. The clip type restricts rendering to the area within the outline of the shape object used to define the clipping path. Any shape object that is used to define the clip. Font attribute is used to convert text string to glyphs. Rendering hints specify preferences in the trade-off between speed and quality. For example, you can specify whether anti-aliasing should be used if this feature is available. As an example, we can consider graphics 2D class. This graphics 2D class extends the graphics class to provide more sophisticated control over geometry, coordinate transformations, color management and text layout. This is the fundamental class for rendering two-dimensional shapes, text and images on the Java platform. This class is in package java.awt. As an example too, we can consider this JavaFX command line option. This configuration basically here prism.order implies which drivers to use. Here you can see J2D, Java 2D. As an exception example, we can consider this exception in canvas rendering when running Java 2D pipeline in the environment with Ubuntu 12.04 and Java version 1.7.0_4.0.4. Java.lang.illegal argument exception, alpha value out of range at java.aw.alpha-composite.init alpha init at java.awt.alpha-composite.get instance alpha-composite .java at java.awt.alpha-composite.drive at com.sun.prism.j2d prism graphics.set extra alpha etc. As an error example, we can consider this exception occurred in canvas rendering when running the Java 2D pipeline in environment with Ubuntu 12.04 and Java version 1.7.0_04. Alpha value out of range and etc. And then com.sun.prism dot j2d prism graphics dot setx extra alpha, etc. Now we are focusing on OpenGL. OpenGL, Open Graphics Library, is a cross-language, cross-platform application programming interface API for rendering 2D and 3D vector graphics. The API is typically used to interact with the graphics processing unit GPU to achieve hardware accelerated rendering. In JavaFX OpenGL on Mac, Linux embedded. Here you can see OpenGL architecture. GPU is connected to display list and polynomial evaluator and per vertex operations and primitive assembly. Immediate mode is passed from CPU to per vertex operations and primitive assembly, and polynomial evaluator interacts with the display list, and polynomial evaluator is connected to per vertex operations and primitive assembly. Per vertex operations and primitive assembly is connected to rasterization. Display list is connected to pixel operations. And pixel operations are connected to texture memory. Pixel operations are going through this path also, and pixel operations are connected to rasterization, and texture memory is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Frame buffer are connected to is connected to pixel operations. In a geometry pipeline, CPU is connected to vertex per vertex operations and primitive assembly through immediate mode, and per vertex operations and primitive assembly is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Here you can see a diagram of the rendering pipeline. The blue boxes are programmable shader stages. The OpenGL rendering pipeline is initiated when you perform a rendering operation Rendering operations require the presence of a properly defined vertex array object and a linked program object or program pipeline object, which provides the shaders for the programmable pipeline stages. Once initiated, the pipeline operates in the following order. 1. Vertex processing. Under that, each vertex retrieve from vertex arrays as defined by the VAO is acted upon the vertex shader. Each vertex in the stream is processed in turn into an output vertex. Then optional primitive tessellation stages and optional geometry shader primitive processing. The output is a sequence of primitives. Step 2, vertex post processing. The outputs of the last stage is adjusted or shipped to a different locations. Transform feedbacks happens here. Primitive assembly, primitive clipping, the perspective divide, and viewport transform to Windows space. Step 3, scan conversion and primitive parameter interpolation, which generate a number of fragments. Step 4, fragment shader processes each fragment. Each fragment generates a number of outputs. Pre-sample processing, including but not limited to scissor test, stencils test, depth test, blending, logical operations, right mask. Vertex specification. The process of vertex specification is where an application sets up an ordered list of vertices to send to the pipeline. These vertices define the boundaries of a primitive. Primitives are basic drawing shapes like triangles, lines, and points. Exactly how the list of vertices is interpreted as primitives is handled via a later stage. This part of the pipeline deals with a number of objects like vertex array objects and vertex buffer objects. Vertex array objects define what data each vertex has, while vertex buffer objects store the actual vertex data itself. A vertex data is a series of attributes. Each attribute is a small set of data that the next stage will do computations on. While a set of attributes do specify a vertex, there is nothing that says that part of a vertex attributes set needs to be a position or normal. Attributes data is entirely arbitrary. The only meaning assigned to any of it happens in the vertex processing stage. Vertex rendering. Once the vertex data is properly specified, then it is rendered as a primitive via a drawing command. Vertex processing. Vertices fetch due to the prior vertex rendering stage begin. They are processing here. Vertex processing stages are almost all programmable operations. This allows user to code to customize the way vertices are processed. Each stage represent different kinds of shade operations. Many of these stages are optional. Vertex shader. Vertex shaders perform basic processing of each individual vertex. Vertex shaders receive the attribute inputs from the vertex rendering and converts each incoming vertex into a single outgoing vertex based on an attribute arbitrary user-defined program. Vertex shaders can have user-defined outputs, but there is also a special output that represent the final position of the vertex. If there is no subsequent vertex processing stages, vertex shaders are expected to fill this position with the clip space position of the vertex for rendering purposes. One limitation on vertex processing is that each input vertex must map to a specific vertex output vertex, and because vertex shader invocations cannot share state between them, the input attributes to output vertex data mapping is one-to-one. That is, if you feed the exact same attribute to the same vertex shader in the same primitive, you will get the same output vertex data. This gives implementations the right to optimize vertex processing. If they can determine if they can detect that they are about to process a previously processed vertex, they can use previously processed data stored in a post transform cache. Thus, they do not have to run the vertex processing on that data again. Vertex shaders are not optional. Tessellation. Primitives can be tessellated using two shader stages and a fixed function tessellator between them. The tessellation control shader TCS stage comes first and determine the amount of tessellation to apply to a primitive, as well as ensuring connectivity between adjacent tessellated primitives. The tessellation evolution shader TES stage comes last, and it applies the interpolation or other operations used to compute user-defined data values for primitives generated by the fixed function tessellation process. Tessellation as a process is optional. Tessellation is considered active if a TES is active. TCS is optional, but TCS can only be used alongside a TES. Geometry shader. Geometry shaders are user-defined programs that process each incoming primitives, returning 0 or more output primitives. The input primitives for geometry shaders are the output primitives from a subset of primitive assembly process. If you send a triangle stripped as a primitive, what the geometry shader will see is a series of triangles. However, there are a number of input primitive types that are defined specifically for geometry shaders. These adjacency primitives give GCs a larger view of primitives. They provide access to vertices of primitives adjacent to the current one. Output of a GS is 0 or more simple primitives, much like the output of primitives at assembly. The GS is able to remove primitives or tessellate them by outputting many primitives for a single input. GCS can also tinker with the vertex values themselves, either doing some of the work for vertex shader or just to interpolate the values when tessellating them. Geometry shaders can even convert primitives to a different types. Input points primitives can become triangles or lines can become points. Geometry shaders are optional. Vertex post-processing. After the shader base vertex processing, vertices undergo a number of fixed function processing steps. Transform feedback. The output of the geometry shader or primitive assembly are written to a series of buffer objects that have been set up for this purpose. This is called transform feedback mode. It allows a user to transform data via vertex or geometry shaders, then hold on to that data for use later. The output, the data output into transform feedback buffer is the data from each primitive emitted by this step. Primitive assembly. Primitive assembly is the process of collecting a run of vertex data output from the prior stage and composing it into a sequence of primitives. The type of primitive the user rendered with determines how this process works. The output of this process is an ordered sequence of simple primitives, lines, points, or triangles. If the output is a triangle strip primitive containing 12 vertices, for example, the output of this process will be 10 triangles. If tessellation or geometry shaders are active, then the limited form of primitive assembly is executed before these vertex processing stages. This is used to feed those particular shader stages with individual primitives rather than a sequence of vertices. The rendering pipeline can also be absorbed at this stage. This allows the use of transform feedback operations without having to actually render something. Clipping. The primitives are then clipped. Clipped mean that primitives that lie on the boundary between the inside of viewing volume and outside are split into several primitives such that the entire primitive lies in the volume. Also, the last vertex processing shader stage can specify user-defined clipping operations on a per vertex basis. The vertex positions are transformed from clip space to window space via a perspective divide and viewpoint transform. Face culling. Triangle primitives can be culled, that is discarded without rendering based on the triangle facing in the window space. This allows you to avoid rendering triangles facing away from the viewer. For closed surfaces, this triangle would naturally be covered up to by triangle facing the user, so there is never any need to render them. Face culling is a way to avoid rendering such primitives. Rasterization. Primitives that reach this stage are then rasterized in order in which they were given. Result of rasterizing a primitive is a sequence of fragments. Fragment is a set of state that is used to composite final data for a pixel or sample if multisampling is enabled in the output frame buffer. The stage for this fragment include its position on the screen space, the sample coverage if multisampling is enabled, and a list of arbitrary data that was output from previous vertex or geometry shader. This last set of data is computed by interpolating between the data values in the vertices for the fragment. The style of interpolation is defined by shader that outputted those values. Fragment processing. The data for each fragment from the rasterization stage is processed by a fragment shader. The output from the fragment shader is a list of colors for each of the color buffers being written to a depth value and a stencil value. Fragment shaders are not able to set the stenciled data for a fragment, but they do have control over the color and depth values. Fragment shaders are optional. If you render without a fragment shader, the depth and stencil values of the fragment get their usual values, but the value of all of the colors that a fragment could have are undefined. Rendering without a fragment shader is useful when rendering only a primitive default depth information to the depth buffer, such as when performing occlusion query test. Pre-sample operations. A fragment data output from the fragment processor is then passed through a sequence of steps. First step is a sequence of culling test. If the test is active, the fragment fails the test. The underlying pixels samples are not updated usually. Many of these tests are only active if the user activates them. The tests are pixel ownership test, fails if the fragment's pixel is not owned by the OpenGL, if another window is overlapping with the GL window. Always passes when using a frame buffer object. Failure means that pixel contains underlying undefined values. Scissor test. When enabled, the test fails if the fragment pixel lies outside of the specified triangle of the screen. Stencil test. When enabled, the test fails if the stencil value provided by the test does not compare as the user specified against the stencil value from the underlying sample in the stencil buffer. Note that stencil value in the frame buffer can still be modified even if the stencil test fails, and even if the depth test fails. Depth test. When enabled, the test fails if the fragment's depth does not compare as the user specified against the depth value from the underlying sample in the depth buffer. Through these are specified to happen after the fragment shader, they can be made to happen before fragment shader under certain conditions. If they happen before fragment shader, then any culling of the fragment will also prevent fragment shader from executing this saving performance. After this, color blending happens. For each fragment color value, there is a specific blending operations between it and the color already in the frame buffer at that location. Logical operations may also take place in lieu of blending, which perform bitwise operation between fragment colors and fragment frame buffer colors. Lastly, the fragment data is written to the frame buffer. Masking operations allow the user to prevent writes to certain values. Color, depth, and stencil write can be masked on and off. Individual color channels can be masked as well. Here you can see a vertex specification is connected to vertex shader. Vertex shader is connected to tessellation. Tessellation is connected to geometry shader. Geometry shader is connected to vertex post processing. Vertex post processing is connected to primitive assembly. Primitive assembly is connected to rasterization. Rasterization is connected to fragment shader. Fragment shader is connected to pre-sample operations. You can see programmable shade stages here: vertex shader, tessellation, geometry shader, and fragment shader. As an example, we can consider this code segment to make sure the JavaFX is using OpenGL Prism backend. So here ES2 is used. As example 2, we can consider this JavaFX 8 command line option. Prism order implies which driver to use. Here ES2, OpenGL ES 2.0. As an error example, we can consider this, and here you can see GOG-AMP.OpenGL.gl drawable imply IMPL.unlock surface at GOG-AMP.OpenGL.gl context IMPL.release, etc. As an error example 2, we can consider this error occurred in environment with Raspberry Pi 2 with Ubuntu 14.04, libegl warning, DRI2 failed to authenticate, failed to create EGL context graphics device, initialization failed for ES2, error initializing quantum renderer, no suitable pipeline found java.lang.runtime exception. Now we are focusing on D3D. Direct 3D is a graphics application programming interface API for Microsoft Windows. Part of DirectX, Direct 3D is used to render three-dimensional graphics in applications where performance is important, such as games. Direct 3D uses hardware acceleration if it is available on the graphics card, allowing for hardware acceleration of the entire 3D rendering pipeline or even only partial acceleration. Direct 3D exposes the advanced graphics capabilities of 3D graphics hardware, including Z buffering, W buffering, stencil buffering, spatial anti-aliasing, alpha blending, color blending, MIP mapping, texture blending, clipping, culling, atmospheric effects, perspective correct texture mapping, programmable HLSL shaders and effects. Integration with the other DirectX technologies enables Direct 3D to deliver such features as video mapping, hardware 3D rendering in 2D overlay planes, and even split providing the use of 2D and 3D graphics in interactive media ties. In JavaFX, DirectX 9 on Windows XP and Windows Vista, DirectX 11 on Windows 7. Here you can see Direct 3D 11 programmable pipeline. Here you can see Direct 3D 11 programmable pipeline. The Direct 3D 11 programmable pipeline is designed for generating graphics for real-time gaming applications. This diagram shows the data flow from input to output through each of the programming stages. The graphics pipeline for Microsoft Direct 3D 11 supports the same stages as Direct 3D 10 graphics pipeline, with additional stages to support advanced features. You can use the Direct 3D 11 API to configure all of the stages that feature common shader cores. The rounded rectangular blocks are programmable by using HLSL programming language. The input assembler stage, the Direct 3D 10 and higher API separates functional areas of the pipeline into stages. The first stage in the pipeline is the input assembler IA stage. The vertex shader stage. The vertex shader VS stage processes vertices from the input assembler, performing per vertex operations such as transformations, skinning, morphing, and per vertex lighting. Vertex shaders always operate on a single input vertex and produce a single output vertex. This vertex shader stage must always be active for the pipeline to execute. If no vertex modification or transformation is required, a pass-through vertex shader must be created and set to the pipeline. Tessellation stage. The Direct 3D 11 runtime supports 3 new stages that implement tessellation, which converts low detail subdivision surfaces into higher detail primitives on the GPU. Tessellation tiles or breaks up higher order surfaces into suitable structures for rendering. Geometry shader stage. The geometry shader GS stage runs application specified shader code with vertices as input and the ability to generate vertices on output. Stream output stage. The purpose of the stream output stage is to continuously output or stream vertex data from the geometry shader stage or vertex shader stage if the geometry shader stage is inactive to one or more buffers in memory. Rasterizer stage. The rasterization stage converts vector information composed of shapes or primitives into a raster image composed of pixels for the purpose of displaying real-time 3D graphics. The pixel shader shader stage. The pixel shader stage (PS) enables rich shading techniques such as per pixel lighting and post-processing. A pixel shader is a program that combines constant variables, texture data, interpolated per vertex values, and other data to produce per pixel outputs. The rasterizer stage invokes a pixel shader once for each pixel covered by a primitive. However, it is possible to specify a null shader to avoid running a shader. Output merger stage. The output merger OM stage generates the final rendered pixel color using a combination of pipeline stage. The pixel data generated by the pixel shaders, the contents of the render targets, and the contents of the depth stencil buffers. The OM stage is the final step for determining which pixels are visible with depth stencil testing and blending the final pixel colors. Here you can see input assembly stage is connected to vertex shader stage. Vertex shader stage is connected to hull shader stage. This hull shader stage is connected to tessellation stage or domain shader stage. Tessellation stage is connected to domain shader stage. Domain shader stage is connected to geometry shader stage, and geometry shader stage is connected to string output stage and rasterizer stage. Rasterizer stage is connected to pixel shader stage. Pixel shader stage is connected to output merger stage. Stream output stage is connected to memory resources. Memory resources buffer texture constant buffer are connected to input assembly stage and vertex shader and hull shader stage and domain shader stage, geometry shader stage, and memory resources interacts with pixel shader stage and output merge stage, and as an example, we can consider this package com.sun.prism.d3d. As an example 2, we can consider this JavaFX 8 command line option prism.order, which implies which driver to use. Here you can see D3D, direct 3D. As an exception example, we can consider this one illegal state exception, which can be occurred in void dispose in D3D pipeline, which is in the package com.sun.prism.d3d. As an error example, we can consider this error message occurred in environment with JavaFX 11 or higher. Graphics device initialization failed for D3D SW. Error initializing quantum renderer. No suitable pipeline found, etc. Now we are focusing on glass windowing toolkit. The glass windowing toolkit is the lowest level in the JavaFX graphics stack. Its main responsibility is to provide native operating services such as managing the windows, timers, and surfaces. It serves as the platform-dependent layer that connects the JavaFX platform to the native operating system. As an example, we can consider this package com.sun.glass. As an example too, we can consider this code segment. Here the abstract class application in the JavaFX application class start and stop methods are called in the JavaFX application thread. The JavaFX application thread is part of the glass window in Toolkit in the com.sun.glass package hierarchy. JavaFX events are processed on the JavaFX application thread. All live scene manipulation must be performed in the JavaFX application thread. Nodes that are not attached to the live scene may be created and manipulated in other threads until they are attached to a live scene. Note the role the glass window in Toolkit plays in the JavaFX application is similar to that of AWT in Swing applications. It provides drawing surfaces and input events from the native platform. Unlike in AWT, where the EDT is different from the native platform's UI thread and communication has to occur between them. The native FX application, the JavaFX application thread in the glass window in Toolkit uses the native platform's UI thread directly. So the abstract class application related to these methods are in com.sun.glass package. Actually, this abstract class application is in package com.sun.glass package hierarchy. As an exception example, we can consider illegal state exception. If the current thread is not the event thread in static void event check static void check event thread method in class application. Now we are focusing on media engine. The media engine component has been designed with performance and stability in mind and provides consistent behavior across platforms. Here you can see classes in the JavaFX.scene.media package. The diagram shows boxes that represent the classes that reside in the JavaFX.scene.media package and the variables that each class includes. The boxes drawn from top to bottom and left to right are labeled media, media player, media view, and media error event. Directional arrows connect the boxes. An arrow points from media box to the media player box. Another arrow points from media player box to media view box, and third arrow points up from the media error event to box to the media player box. The media class variables are duration, error, width, height, and on error. The media player class variables are status, volume, rate, autoplay, balance, mute, start time, stop time, total duration. The media view class variables are media, media player, x, y, smooth, viewport, reserve, preserve ratio, fit height, and fit width. The JavaFX media concept is based on the following entities: media, the media resource containing information about the media, such as its source, resolution, and metadata. Media player, the key component providing the controls for playing media. Media view, a node object to support animation, translucency, and effects. Each element of the media functionality is available through the JavaFX API. This figure shows the classes that reside in the JavaFX.scene.media package. These classes are interdependent and are used in combination to create an embedded media player. The media player class provides all the attributes and functions needed to control media playback. You can either set autoplay mode, call the play function directly, or explicitly specify the number of times that the media should play. The volume variable and the balance variable can be used to adjust the volume level and right and left right settings respectively. Volume level range is from 0 to 1.0, the maximum value. The balance range is continuous from minus 1.0 on the far left, 0 at the center, and 1.0 at the right. The play, stop, and pause functions control media playback. Additionally, a bundle of functions handle a specific event when the player does one of the following: buffers data, reaches the end of media, stalls because it has not received data far enough to continue playing, encounters any of the errors defined in the media error event class. Media view class extends the node class and provide a view of the media being played by the media player. It is responsible mostly for effects and transformations. Its media player instance variable specifies the media player object by which the media is being played. Other Boolean attributes serve to apply the particular effect provided by the node class. For example, to enable the media player to be rotated. Here you can see media is connected to media player, media error event is connected to media player, and media player is connected to node. As an example, we can consider this package JavaFX.scene.media provides the set of classes for integrating audio and video into JavaFX applications. The primary use for this package is media playback. There are three principal classes in the media package: media, media player, and media view. As an example 2, we can consider this code segment. The class media player the media player class provides the control for playing media. It is used in combination with media and media view class. To display and control media playback. Media player does not contain any visual elements, so must be used with the media view class to view any video track which may be present. Media player is in the package javafx.scene.media. Here you can see a set cycle count method. Set the cycle count. Its effect will be constrained to 1 to integer.max value. Invoking this method will have no effect if media duration is duration.indefinite. Here the value is 50,000. Here the set rate method set the playback rate to the supplied value, here 4. Its effect will be clamped to the range 0.0 to 8.0. Invoking this method will have no effect if the media duration is duration.indefinite. The play method starts the playing media. If previously paused, then playback resumes where it was paused. If the playback is stopped, playback start from the start time. When playing actually start, the status will be set to media player.status.playing. Here the media view, a node that provides a view of media being played by media player. This following code snippet illustrate error handling with media. Errors using JavaFX media may be either synchronized or asynchronized. In general, synchronized errors will manifest themselves as an exception. And asynchronous errors will cause a JavaFX property to be set. In the latter case, either the error property may be observed directly an on error callback registers, or possibly both. The main sources of synchronous errors are media, and media player, the asynchronous errors properties are media.error and media player.error, and the asynchronous error callbacks media dot on error and media player dot on error and media view dot on error. Some errors might be duplicated. For example, a media player will propagate an error that encounters to its associated media and media player to all its associated media views. As a consequence, it is possible to receive multiple notifications of the occurrence of a given error depending on which properties are monitored. Here you can see the section handle asynchronous error in media object. Here handle asynchronous error in media player object. And here handles asynchronous error in media view. Here handle asynchronous. Here handle synchronous error creating media player. And here handle exception in media player constructor. And here handle synchronous error in creating media. Handle exception in media constructor. As an exception example, we can consider class media exception. A media exception describes a runtime error condition in a media player, or media view. This class is in package JavaFX.scene.media. As an error example, we can consider this error occurred on line import JavaFX.scene.media. The error package JavaFX.scene.media does not exist. Now we are focusing on web engine. This web engine component is based on WebKit, which is an open source web browser engine that supports HTML5, CSS, JavaScript, DOM, and SVG. It enables developers to implement the following features in their Java applications: render HTML content from local or remote URL, support history and provide back and forward navigation, reload the content, apply effect to the web component, edit the HTML content, execute JavaScript commands, handle events. Here you can see a architecture of embedded browser and its relation to other JavaFX classes. Here you can see the scene graph here. In the JavaFX WebView is a mini browser, also called an embedded browser, that provides a web viewer and full browsing functionality to its API in JavaFX application. This browser is based on WebKit, that is an open source web browser engine that supports HTML5 and JavaScript, CSS, DOM rendering, and SVG graphics. The WebView class is an extension of the Node class. Here the web engine is a non-visual object capable of managing one web page at a time and provides basic web page functionality through its API. It supports user interaction such as navigation, links, and submitting HTML forms, although it does not interact with users directly. It loads web pages, creates their direct models, applies styles as necessary, and runs JavaScript on pages. It provides access to the document model of the current page and enables two-way communication between Java application and JavaScript code of the page. It wraps web page object which provide interaction with the native WebKit core. So here you can see scene, group, node, web view, and nodes are in scene graph, and scene is connected to group, node, and web view. Group is connected to nodes. Web view interacts with the web engine. As an example, we can consider this class web engine. Web engine is a non-visual object capable of managing one web page at a time. It loads web pages, creates their document models, applies styles as necessary, and runs JavaScript on pages. It provides access to the document model of the current page and enables two-way communication between a Java application and JavaScript code of the page. This class is in the package javafx.scene.web. The following example changes the stage title. When loading completes successfully. The method final worker void get load worker get load worker returns a worker object that can be used to track loading loading progress. Here the state property gets the read-only object property representing the current state. The web engine class provide two ways to load content into a web engine object from an arbitrary URL using the load java.land.string method. This method uses the java.net package for network access and protocol handling. From an in-memory string using the load content, java.land.string and java.land.string and load content java.land.string methods. Loading always happens on a background thread. Methods that initiate loading return immediately after scheduling a background job. To track the progress and or cancel a job, use worker instance available from get load worker method. Here you can, as an example 3, we can consider this code segment. Create a web view, web engine objects and load via remote URL. The class web view is a node that manages a web engine and displays its contents. The associated web engine is created automatically at construction time and cannot be changed afterwards. WebView handles mouse and some keyboard events and manages scrolling automatically, so there's no need to put it into a scroll pane. WebView is in the package javafx.scene.web. Here you can see a create a web view and get web engine via WebView and load URL. As an example, we can exception example, we can consider runtime exception, which can be occurred in the method final string property user style sheet location property in class web engine. As an error example, we can consider this error occurred in the environment with semantic endpoint protection manager 14.3. The given URL is not valid, null. The given URL is not valid, could not initialize class javafx.scene.web.webengine. Now we are focusing on JDK API libraries and tools. JDK API libraries and tools. Here you can see conceptual diagram illustrating the components of Oracle's Java SC products. Here we are considering edition Java Platform Standard Edition 8. Oracle has two products that implement Java Platform Standard edition, Java SC8, Java SC Development Kit, JDK, and Java SC Runtime Environment, JRE8. JDK 8 is a superset of JRE8, contains everything that is in JRE8 plus tools such as compilers and debuggers, necessary for developing applets and applications. JRE8 provides the libraries, the Java virtual machine, um, JVM and other components to run applets and application written in Java programming language. Note that the JRE includes components not required by the JavaSC specification, including both standard and non-standard Java components. The Java conceptual diagram categorizes Java component technologies in levels. The technologies that are part of a lower level serves as the foundation for those that are part of higher level. Java language, tools and APIs, deployment and user interface toolkits, integration libraries, other base libraries, lang and util base libraries, Java virtual machine. JDK consists of all levels. JRE consists of the following level: deployment, user interface toolkit, integration libraries, other base libraries, and lang and util base libraries. JavaFX API consists of following levels: deployment, no, sorry, not deployment is not included. User interface toolkits, except JavaFX, integration libraries, other base libraries, and lang and util base libraries. Compact profiles consist of the following levels: integration libraries, other base libraries, and lang and util base libraries. JDK Java SC Development Kit. JDK includes the JRE plus command line development tools such as compilers and debuggers that are necessary or useful for developing applets and applications. JRE Java SC Runtime Environment. The JRE provides the libraries, Java Virtual Machine, and other components necessary for you to run applets and application written in Java programming language. This runtime environment can be redistributed with applications to make them freestanding. Java SC API, Java Platform Standard 8 API specification. Compact profiles. Compact profiles introduced in JDK 8 enable reduced memory footprints for applications that do not require the entire Java platform. The Java C compiler has a dash profile options, which allows the application to be compiled using one of the supported profiles. Java language. A Java programming language is a general-purpose, concurrent, strongly typed, class-based, object-oriented language. It is normally compiled to the bytecode instruction set and binary format defined in the Java Virtual Machine specification. Java JDK tools and utilities. Java launches a Java application. The Java command starts a Java application. It does this by starting a Java runtime environment, JRE, loading the specified class and calling the class's main method. The method must be declared public and static. It must not return any value, and it must accept a string array as a parameter. Java C, the Java programming language compiler, Java C. The Java programming language compiler, Java C, reads source files written in the Java programming language and compiles them into bytecode class files. Optionally, the compiler can also process annotations found in source and class files using pluggable annotation processing API. The compiler is a command line tool but can also be invoked using Java Compiler API. The compiler accepts source code defined by the Java language specification, JLS, and produces class files defined by the Java Virtual Machine specification, JVMS. Java Doc. The Java Doc is a tool that passes the declarations and documentation commands in a set of source files and produces a set of HTML pages describing the classes, interfaces, constructors, methods, and fields. You can use a Java doclet to customize Java doc output. A doclet is a program written with the doclet API that specifies the content and format of the output to be generated by the tool. You can write a doclet to generate any kind of text file output such as HTML, HGML, XML, RTF, and MIF. Oracle provides a standard doclet for generating HTML format API documentation. Doclets can also be used to perform special tasks not related to producing API documentation. Java Archive, Java Files. Java Archive is a platform independent file format that aggregates many files into one. Multiple Java applets and their request components, .class files, images, and sounds can be bundled in a Java file and subsequently downloaded to a browser in a single HTTP transaction, greatly improving the download speed. The Java format also supports compression, which reduces the file size, further improving the download time. In addition to applets, author can digitally sign individual entries in a Java file to authenticate their origin. It is fully extensible. Java P deassembles one or more class files. Java P command deassembles one or more class files. The output depends on the options used. When no options are used, then the Java P command prints the package, protected and public fields, and methods of the classes passed to it. The Java P command prints its output to std out. JDEPS, Java Class Dependency Analyzer. The JDEPS command shows the package level or class level dependencies of class files. The input class can be a path name to a .class file, a directory, or a Java file, or it can be fully qualified class name to analyze all class files. The options determine the output. By default, JDEPS outputs the dependencies to the system out. It can generate the dependencies in dot language. Scripting Java Web Services Tools, schema generator for Java architecture for XML binding, WSGen tool to generate JAX, WS portable artifacts, WS import tool to generate JAX WS portable artifacts, XJC binding compiler for Java architecture for XML binding. Security. These security tools help you to set security policies on your system and create applications that can work within scope of security policies set at remote sites. Key tool, manage keystrokes and certificates. JAR signer, generate and verify JAR signatures. Policy tool, GUI tool for managing policy files. Monitoring tools, you can use the following tools to monitor JVM performance statistics. The tools described in these sections are unsupported and experimental and should be used with that in mind. They may not be available in future JDK versions. These tools are supported on all platforms except Windows 98 and Windows ME. JPS, experimental JVM process status tool, list instrumental hotspot Java virtual machines on target system. JStat, experimental JVM statistics monitoring tool, attaches to an instrumental hotspot Java virtual machine and collects and logs performance statistics as specified by the command line options. JStatD, experimental JVM JStat daemon launches RMI server application that monitors for the creation and termination of instrumental hotspot Java virtual machines and provide an interface to allow remote monitoring tools to attach to a Java virtual machine running on local system. JConsole, a JMX compliant graphical tool for monitoring a Java virtual machine. It can monitor both local and remote JVMs. It can also monitor and manage an application. Java Visual VM. Java Visual VM is a tool that provides a visual interface for viewing detailed information about Java applications while they are running on a Java virtual machine JVM, and for the troubleshooting and profiling these applications. Various optional tools including Java VM are provided with the Java Development Kit JDK for retrieving different types of data about running JVM software instances. For example, most of the previously standalone tools, JConsole, JStat, JInfo, JStack, and JMap are part of Java Visual VM. Java Visual VM federates these tools to obtain data from the JVM software, then reorganizes and presents the information graphically to enable you to view different data about multiple Java applications uniformly, whether they are running locally or remote machines. Furthermore, developers can extend the Java VM to Java Visual VM to add new functionality by creating and posting plugins to the tool's built-in update center. JMC, JDK Mission Control. JDK Mission Control, JMC, is an advanced set of tools for managing, monitoring, profiling, and troubleshooting Java applications. JMC enables efficient and detailed data analysis for areas such as code performance, memory, and latency without introducing the performance overhead normally associated with profiling and monitoring tools. JFR, Java Flight Recorder, is a tool for collecting diagnosis and profiling data about a running Java application. It is integrated into Java Virtual Machine and causes almost no performance overhead, so it can be used even in heavily loaded production environment. The default settings are used both internal testing and customer feedback. Internal testing and customer feedback indicate that performance impact is less than 1%. For some applications, it can be significantly lower. However, for short-running applications, which are not a kind of applications running in the production environments, relative startup and warm-up times can be larger, which might impact the performance by more than 1%. JFR collects data about the JVM as well as the Java application running on it. JPDA, Java Platform Debugger Architecture. The Java Platform Debugger Architecture, JPDA, consists of three interfaces designed for use by debugger in development environment for desktop systems. The Java Virtual Machine Tools interface, JVM TI, defines the services a VM must provide for debugging. Java Debug Via Protocol, JDWP, defines that the format of information and requests transferred between processing being debugged and debugger frontend, which implements Java Debug Interface, JDI. Java Debug Interface defines information and request at the code level. JVM TI, Java Virtual Machine Tool Interface. The JVM Tool Interface, JVM TI, is a native programming interface for use by tools. It provides both a way to inspect an state and to control execution of applications running in the Java Virtual Machine JVM. JVM TI supports full breadth of tools that need access to JVM state, including but not limited to profiling, debugging, monitoring, thread analysis, and coverage analysis tools. Java IDL and RMI IOP tools. These tools are used when creating applications that use OMG standard IDL and COBA IOP. TNAM ERV provide access to the naming service. IJ generates .java files that map an OMG IDL interface and enable an application written in the Java programming language to use COBA functionality. ORBD provides support for clients to transparently locate and invoke persistent objects on servers in the COBA environment. Server tool provides ease of use interface for application programmers to register, unregister, start up and shut down a server. Remote method invocation, RMI tools. These tools help to create applications that interact over the web or other networks. RMIC generates stubs and skeleton for remote object. RMI registry, remote object registry service. RMID, RMI activation system daemon. Serial VER, returns class serial version UID. JavaDB 10.11 document. It's a JavaDB is a relational database management system that is based on Java programming language. Java deployment tools, utilities for use in conjunction with deployment of Java applications and applets on the web. Java packager, perform tasks related to packaging and signing Java and JavaFX applications. Pack 200, transform a Java file into a compressed Pack 200 file using Java gzip compressor. Compressed packed files are highly compressed Java, which can be directly deployed, saving bandwidth and reducing download time. Unpack 200, transform a packed file produced by Pack 200 into Java file. Internationalization tools. This tool helps to create localizable applications. Native to ASCII, convert text to Unicode Latin 1. Web services tools. Schema generator for Java architecture for XML binding. VS Gen, tools to generate Java WS portable artifacts. Sorry, it's WS Gen. WS import, tool to generate WS portable artifacts. XJC, binding compiler for Java architecture for XML binding. Here in scripting, following tools can be used to run scripts that interact with the Java platform. JJS runs the nashorn command line script shell. JRun script, experimental script shell for Java, runs a script. This tool is unsupported and experimental in nature and should be used within that in mind. It might not be available in future JDK versions. Troubleshooting tools. The following tools can be used for specified troubleshooting tasks. The tools described in this section are unsupported and experimental in nature and should be used with that in mind. They may not be available in future JDK versions. Some of these tools are not currently available on Windows. JInfo, experimental configuration info for Java, prints configuration information for a given process or core file or a remote debug server. JHat, experimental heap dump browser, start a web server on the heap dump file, for example produced by jmap dump, allowing the heap to be browsed. JMap, experimental memory map for Java, prints shared object memory maps or heap memory details of a given process, core file or remote debug server. JSA debug D, Experimental serviceability agent debug daemon for Java attaches a process or core file that acts as a debug server. JStack experimental stack trace for Java prints a stack trace of threads for given process or core file or remote debug server. Deployment. Have an application ready to publish. Follow these steps for basic deployment. Step 1, decide how you want users to access and run your application. Step 2, create the application package. Step 3, set up the web page, or if your application is embedded in a web page or is launched from the browser. Step 4, copy the package to the location from which you want users to access it. Java Web Start. Java Web Start is an application deployment technology that gives you the power to launch full-featured applications with a single click from your web browser. You can now download and launch applications such as complete spreadsheet program or internet chat client without going through complicated installation procedures. Java applet and Java plugin. Java plugin technology, hereafter the Java plugin, which is included in the Java runtime environment JRE, enables Java applets to run in web browsers on desktop. Java plugin provides powerful capabilities to applets in the web browser while improving overall reliability and functionality of applets in a backward compatible manner. User interface libraries. Swing implements a set of components for building graphical user interfaces, GUIs, and adding rich graphics functionality and interactivity to Java applications. Swing components are implemented entirely in the Java programming language. The pluggable look and feel lets you to create GUIs that can either look the same across platforms or can assume the look and feel of the current OS platform, such as Microsoft Windows, Solaris, or Linux. Java 2D graphics and imaging. Java 2D API is a set of classes for advanced 2D graphics and imaging. It encompasses line art, text, and images in a single comprehensive model. The API provides extensive support for image composing and alpha channel images, a set of classes to provide accurate color space definition and conversion, and a rich set of display-oriented imaging operations. These classes are provided as additions to the java.awt and java.awt.image packages. Abstract Window Toolkit AWT. The Abstract Window Toolkit supports graphical user interface GUI programming. AWT features include a set of native user interface components, a robust event handling model, graphics and imaging tools, including shape, color, and font classes, layout managers for flexible window layouts that do not depend on a particular window size or screen resolution, data transfer classes for cut and paste through the native platform clipboard. Accessibility, Java accessibility guide. enabling accessibility. If you have a Java application that was designed for use the Microsoft Windows accessive technology and program and Java Accessibility API JAAPI program. With the Java Accessibility API, developers can easily create Java applications that are accessible to persons with disabilities. Drag and drop. Drag and drops enables data transfer across Java programming language and native applications, between Java programming language applications and within single Java programming language applications. The Java Input Method Framework IMF technology. The input method framework enables the collaboration between text editing components and input method for entering text. Input methods are software components that let the user enter text in ways other than simple typing on a keyboard. They are commonly used to enter Japanese, Chinese, or Korean languages using thousands of different characters on keyboards with far fewer keys. However, the framework also support input methods for other languages and the use entirely of different input mechanisms such as handwriting or speech recognition. Java Image I/O technology. Java Image I/O API developed through JSR 015 provides a pluggable architecture for working with images stored in files and accessed across the network. It offers substantially more flexibility and power than the previous APIs for loading and saving images. The API provides a framework for the addition of format-specific plugins. Plugins for several common formats are included with Java Image I/O, but third parties can use this API to create their own plugins to handle special formats. Java Print Service. The Java Print Service API allows printing on all Java platforms, including requiring a small footprint such as a Java ME profile, but also support the java.awt.print.print job API. The Java Print Service API includes an extensible print attribute set based on the standard attributes specified in the internal printing protocol IPP 1.1 from the IETF. With the attributes, client and server applications can discover and select printers that have the capabilities specified by attributes, in addition to the included Stream Print Service, which allows applications to transcode data to different formats. Third parties can dynamically install their own print services through the service provider interface. Java Sound technology. The Java platform includes powerful API for capturing, processing, and playing back audio and MIDI musical instrument digital interface data. This API is supported by an efficient sound engine which guarantees high quality audio mixing and MIDI synthesis capabilities for the platform. Integration libraries. IDL Java IDL technology adds COBA common object request broker architecture capability to the Java platform, providing standard-based interoperability and connectivity. Java IDL enables distributed web-enabled Java application to transparently invoke operations on remote network services using the industry standard IDL Object Management Group Interface Definition Language, and IIOP Internet Inter-ORB Protocol defined by the Object Management Group. Runtime components includes a Java ORB for distributed computing using IIOP communication. Java JDBC API. The Java database connectivity JDBC API provides universal data access from Java programming language. Using the JDBC API, you can access virtually any data source from relational databases to spreadsheet and flat files. JDBC technology also provides the common base on which tools and alternative interfaces can be built. Java Naming and Directory Interface JNDI. The Java Naming and Directory Interface JNDI provides naming and directory functionality to applications written in Java programming language. It is designed to be independent of any specific naming or directory service implementation. Thus, a variety of services, new, emerging, and already deployed ones, can be accessed in a common way. RMI, Java Remote Method Invocation API, Java RMI. Java Remote Method Invocation, Java RMI enables the programmer to create distributed Java technology-based applications in which the methods of remote Java objects can be invoked from other Java virtual machines, possibly on different hosts. RMI uses object serialization to marshal and unmarshal parameters and does not truncate types, supporting true object-oriented polymorphism. Java RMI over IIOP, Java Remote Method Invocation over Inter-ORB Protocol Technology, RMI IIOP, is a part of Java Platform Standard Edition Java SC. RMI programming model enables the programming of COBA servers and applications via RMI API. You can choose to work completely within the Java programming language using Java Remote Method Protocol JRMP as the transport, or work with other COBA compliant programming languages using Inter-ORB Protocol IIOP. Scripting for Java Platform. Many implementations of scripting and dynamically typed languages generate Java bytecode so that programs can be run on the Java platform, just as are actual Java programs. Implementing a language in this way, or as a Java interpreter class for scripting language, provides all the advantages of Java platform. Scripting implementations can take advantage of the Java platform's binary portability, security, and high performance bytecode execution. Other base libraries. Java Beans Component API. The Java Beans Component API extends the Java platform write once, run anywhere capability to reusable components development. In fact, the Java Beans architecture takes interoperability a major step forward. Your code can run on every OS and also within any application environment. A developer can create component based on the Java Beans architecture. Beans secure a future in emerging network software market without losing customers that use proprietary platforms, because Beans interoperate with ActiveX, OpenDoc, and Live Connect. Long-term persistence for Beans, Java Beans enables you to read and write Beans as a textual representation of its property values. Security. Java security technology include a large set of APIs, tools, and implementations of commonly used security algorithms, mechanisms, and protocols. Java security APIs span a wide range of areas, including cryptography, public key infrastructure, secure communication, authentication, and access control. Java security technology provides the developer with a comprehensive security framework for writing applications and also provides the user or administrator with a set of tools to securely manage applications. Uh, Java object serialization. Object serialization supports the encoding of objects and objects reachable from them into a stream of bytes. Serialization also supports the complementary reconstruction of the object graph from a stream. Serialization is used for lightweight persistence for communication via sockets, so Java remote method invocation, Java RMI. The default encoding of objects protect private and transit data and supports evolution of classes. A class may implement its own external encoding and is then solely responsible for the external format. Extension mechanism for support of optional packages. This feature has been deprecated and will be removed in future release. Optional packages are packages of classes and any associated native code that application developer can use to extend the functionality of the core platform. The extension mechanism allows the Java virtual machine VM to use classes of optional extension in much the same way as the VM uses classes in the Java platform. The extension mechanism also provides a way to wait for needed optional packages to be retrieved from specified URLs when they are not already installed in the JDK or JRE. Java Management Extensions JMX. The Java Management Extensions JMX API is a standard API for management and monitoring of resources such as applications, devices, services, and Java Virtual Machine. The JMX technology was originally developed through the Java Community Process (JCP) as Java Specification Request JSR3, Java Management Extensions, and JSR 160 JMX Remote API. XML in Java SC. XML extensible markup language is a flexible way to create common platform formats to and share both the format and the data on the World Wide Web, intranets, and elsewhere. XML can be used by any individual or group of individuals or companies that wants to share information in a consistent way. Networking, Java networking, Java.NET package, JavaX.NET package, JavaX.NET SSL package, com.sun.net.http server package, com.sun.net.http server.spi package, JDK.NET package. Java endorses standards override mechanism. This feature will be is deprecated and will be removed in future release. For time to time, it is necessary to update the Java platform in order to incorporate newer versions of standard that are created outside of the Java community process, endorse standard, and or in order to update the version of a technology included in the platform correspond to a later standalone version of the technology. The endorse standards override mechanism provides a means whereby the later versions of classes and interfaces that implement endorse standard or standalone technologies may be incorporated into the Java platform. Java Native Interface. Java Native Interface JNI is a standard programming interface for writing Java native methods and embedding Java virtual machine into native applications. The primary goal is binary capability of native method libraries across all Java virtual machine implementations on a given platform. Java date and time packages. The datetime APIs introduced in JDK 8 are a set of packages that model the most important aspect of Java of date and time. The core classes in the Java.time package use the calendar system defined in ISO 8601 based on the Gregorian calendar system as a default calendar. Other non-ISO calendar systems can be represented using java.time.chrono package, and several predefined chronologies such as Hiraj and Thai Buddhist are provided. Java IO, NIO, and NIO.2. Java IO support is included in the Java IO and Java NIO packages. Together, these packages include following features: input and output through data streams, serialization and file system, charsets, decoders, encoders for translating between bytes and Unicode characters, access to file attributes and file systems, APIs for binding scalable servers using asynchronous or multiplex non-blocking I/O. Java internationalization support. Internationalization is the process of designing an application so that it can be adapted to various languages and regions without engineering changes. Sometimes the term internationalization is abbreviated as I18N because there are 18 letters between the first I and the last N. Lang and util packages provides the fundamental object and classes, wrapper classes for primitive types, and a basic math class, and more. Core Java Math. The math functionality includes the floating point libraries java.lang.math and java.lang.strictmath, and arbitrary position math java.math package. The collections framework. The collections framework is a unified architecture for representing and manipulating collections, enabling them to be manipulated independently of details of their representation. It reduces programming effort while increasing performance. It enables interoperability among unrelated APIs, reduces effort in designing and learning new APIs, and fosters software reuse. The framework is based on more than a dozen collection interfaces. It includes implementation of these interfaces and algorithms to manipulate them. Package java.lang.ref. Provide reference object classes which support a limited degree of interaction with garbage collector. Regular expressions package java.util.regex classes for matching character sequences against patterns specified by regular expressions. Java logging technology. The Java logging API is introduced in package java.util.logging facilitates software servicing and maintenance at customer sites by producing log reports suitable for analysis by the end users, system administrators, field service engineers, and software development teams. The logging APIs capture information such as security failures, configuration errors, performance bottlenecks, and or bugs in the applications or platforms. Monitoring and management for Java platform. The Java Platform Standard Edition provides comprehensive monitoring and management support for the platform. Instrumentation java.lang.instrument package. Java.lang.instrument package provides a Java programming language API for tools to instrument Java programming language applications, for example, to monitor them or collect performance information. Tools use java.lang.instrument to modify the class file that define the class, generally by inserting into the bytecode of methods additional bytecode which perform instrumentation. Java concurrency utilities. The concurrency utilities package provide powerful extensible framework of high performance thread utilities such as thread pools and blocking queues. This package frees the programmer from the need to craft these utilities by hand in much same manner the collections framework did for data structures. Additionally, these packages provide low-level primitives for advanced concurrent programming. The Java Reflection API. The reflection enables Java code to discover information about the fields, methods, and constructors of load classes and use reflected fields, methods, and constructor to operate on their underlying counterparts within security restrictions. The API accommodates applications that need to access to either the public members of the target object based on its runtime class or the members declared by a given class. It also allows programmers to suppress default reflective access control. The package version identification versioning. The versioning feature enables package level version control so that applications and applets can identify the runtime version the version of a specific Java runtime environment's VM and class package. Core Java Preferences API. Applications require preference and configuration data to adapt to the needs of different users and environment. The java.util.prefs package provides a way for applications to store and retrieve the user and system preference and configuration data. The data is stored persistently in an implementation dependent backing store. There are two separate trees of preference nodes, one for user preference and one for system preference. Java Archive, Java files. The Java Archive is a platform independent file format that aggregate many files into one, multiple Java applets, and their request component. Class files, images, and sound can be bundled in a Java file and subsequently loaded to a browser in a single HTTP transaction, greatly improving the download speed. The Java format also supports compression, which reduces the file size further improving the download time. In addition, the applet author can digitally sign individual entries in a jar file to authenticate their origin. It is fully extensible. The package java.util.zip provide classes for reading and writing standard zip and gzip file format. Also include classes for compressing and decompressing data using the deflate compression algorithm, which is used by the zip and gzip file format. Additionally, there are utility classes for computing the CRC32 and EDLER32 checksums of arbitrary input streams. Java virtual machine technology. The JDK provide one or more implementation of Java virtual machine. On platform typically use the client applications. The JDK comes with the VM implementation called Java Hotspots client VM. The client VM is tuned for reducing the startup time and memory footprint. It can be invoked by the client command line option when launching the application. On all platforms, JDK comes with an implementation of a Java virtual machine called Java Hotspot Server VM. The server VM is designed for maximum program execution speed, so it can be invoked by using the -server command line option when launching the application. And you can also see JavaFX here. JavaFX is a set of graphics and media packages that enable developers to define, create, and test and debug and deploy rich client applications that operate consistently across diverse platforms. Here you can see JDK and JRE and compact profiles and JavaFX API. In Java languages, you can see Java language, tools and API, Java, JavaC, JavaDoc, JavaP, JDEPS, scripting, security monitoring, JConsole, JavaVM, JMC, JFAR, JDPA, JPDA, JVM, TI, IDL, RMI, Java DB, deployment, internationalization, web services, troubleshooting, and deployment, Java Web Start, Applet, Java plugin, and JavaFX, user interface toolkits, Swing, Java 2D, AWT, accessibility, drag and drop, input methods, image IO, print service, and sound. Integration libraries, IDL, JDBC, JNDI, RMI, IOP, and scripting. Other base libraries are Beans, security, serialization, extension mechanism, JMX, XML, JAXP, networking, override mechanism, JNI, date and time, input output, internationalization. Java Lang and utils, Java Lang and util base libraries, math collections, reference REF objects, regular expressions, logging, management, instrumentation, concurrency utilities, reflection, versioning, preferences, API, JavaShip, Java virtual machine, Java hotspot client, and server VM. As an example, we can consider java.lang package. Provides classes that are fundamental to the design of the Java programming language. Java, as example 2, we can consider JavaC, the programming language compiler JavaC. The programming language compiler JavaC reads source files written in the Java programming language and compiles them into bytecode class files. Optionally, the Java compiler can also process annotations found in source and class files using pluggable annotation processing API. The compiler is a command line tool but can also be invoked using Java Compile API. The compiler accepts source code defined by the Java language specification JLS and produces class files defined by Java Virtual Machine specification JVMS. Exception example, class exception. The class exception and its subclasses are a form of throwable that indicates condition that a reasonable application might want to catch. This is in package java.lang. Now we are focusing on Java Virtual Machine. A Java Virtual Machine, JVM, is a virtual machine that enables a computer to run Java programs as well as programs written in other languages that are also compiled to Java bytecode. The JVM is detailed by a specification that formally describes what is required in a JVM implementation. Having a specification ensures interoperability of Java programs across different implementation, so that program authors using the Java Development Kit JDK need not worry about idiosyncrasies of the underlying hardware platform. Here you can see the JVM architecture diagram. A virtual machine is a software implementation of physical machine. Java was developed with the concept of WORA, write once, run anywhere, which runs on a VM. The compiler compiles the Java files into a java.class file. Then that .class file is input into JVM, which loads and executes the class files. As shown in this diagram, JVM is divided into three main subsystems: class loader subsystem, runtime data area, and execution engine. Class loader subsystem. The Java's dynamic class loading functionality is handled by the class loader subsystem. It loads links and initialize the class file when it refers to a class for the first time at runtime, not compile time. Loading classes will be loaded by this component. Bootstrap class loader extension, class loader and application class loader are the three class loaders that will help in achieving it. Bootstrap class loader, responsible for loading classes from the Bootstrap class path. Nothing but rt.jav highest priority will be given to this loader. Extension class loader, responsible for loading classes which are inside the ext folder jre /lib. Application class loader, responsible for loading application level class path mention, environment variables, etc. These class loaders will follow delegation hierarchy algorithm while loading the class files. Linking verify, bytecode verify will verify whether the generated bytecode is proper or not. If the verification fails, we will get the verification error. Prepare, for all static variables, memory will be allocated and assigned with default values. Resolved, the all symbolic memory references are replaced with the original references from method area. And initialization, this is the final phase of class loading. Here all static variable will be assigned with the original values and the static block will be executed. Runtime data area. The runtime data area is divided into 5 major components. Method area, all the class level data will be stored here, including static variables. There is only one method area per JVM and it is a shared resource. Heap area, all the objects and their corresponding instance variables and arrays will be stored here. These are also one heap area per there is also one heap area per JVM. Since the method and heap areas share memory for multiple threads, the data stored is not thread safe. Stack area, for every thread a separate runtime stack will be created. For every method call, one entry will be made in the stack memory, which is called stack frame. All local variables will be created in the stack memory. The stack area is thread safe since it is not shared resource. The stack frame is divided into 3 sub entries: local variable array, related to the method how many local variables are involved and the corresponding values will be stored here. Operand stack, if any immediate operation is required to perform, operand stack acts as a runtime workspace to perform the operation. Frame data, all symbols corresponding to the method is stored here. In case of any exception, the catch block information will be maintained in the frame data. PC registers, each thread will have separate PC registers to hold the address of current execution instruction. Once the instruction is executed, the PC register will be updated with the next instruction. Native method stack. Native method stack holds native method information. For every thread, a separate native method stack will be created. Execution engine. The bytecode which is assigned to the runtime data area will be executed by execution engine. The execution engine reads the bytecode and execute it piece by piece. Interpreter. The interpreter interprets the bytecode faster but executes slowly. The disadvantage of the interpreter is that when one method is called multiple times, every time a new interpretation is required. JIT compiler. The JIT compiler neutralizes the disadvantage of the interpreter. The execution engine will be using the help of the interpreter in converting bytecode, but when it finds repeated code, it uses JIT compiler, which compiles the entire bytecode and changes it to a native code. This native code will be used directly for repeated method calls, which improve the performance of the system. Intermediate code generator produces intermediate code. Code optimizer, responsible for optimizing the intermediate code generated above. Target code generator, special responsible for generating machine code for native or native code. Profiler, a special component responsible for finding hotspots, that is whether the method is called multiple times or not. A profile is here. Garbage collector collects and removes unreferenced objects. Garbage collection can be triggered by calling system.gc, but the execution is not guaranteed. Garbage collection of the JVM collects the objects that are created. JNI, Java native interface. JNI will be interacting with the native method libraries and provide native libraries required for execution engine. Native method libraries. This is a collection of native libraries which is required for the execution engine. Here you can see class loader subsystem interact with stack runtime data areas. Runtime data areas interacts with execution engine, and native method interface. Class file is connected to class loader subsystem. Loading is connected to linking. Linking is connected to initialization in class loader subsystem. Bootstrap class load is connected to execution class loader. Execution class load is connected to application class loader. Verify is connected to prepare. Prepare is connected to resolve. Method area, heap area, stack area, and PC register and native method stacks are in stack and in runtime data areas. Threads are in stack area. In thread, stack frame, LVA, OS, and PD, FD frame data and are there. PC register for thread 1, PC register for thread 2, and PC register for thread N, and there are in PC registers. Interpreter, GIT compiler, and garbage collections are in execution engine. In JDK compiler, intermediate code generator is connected to code optimizer. Code optimizer is connected to target code generator, and profile also in JIT compiler. And execution engine is execution engine interacts with native method interface. Native method interface interacts with native method library. As an example, we can consider this standard options for Java VM. Java VM options: module dash module dash path, module path, or dash p module path, semicolon separated list of directories in which each directory is a directory of modules. Standard options for Java dash add dash modules. Module specifies the root modules to resolve in addition to the initial module. Modules also can be all default, all system, and all module path. As an error example, we can consider the error occurred with this JVM options. In this specific case, error could not create the Java virtual machine. Error, a fatal exception has occurred. Program will exit. This is end of my presentation. Thank you very much for watching.